All right, so while most of our limits are going to work, all the limit techniques and tricks that we used before, all the limit laws are still going to apply for limits of our sequences, there are some little tips and tricks that you want to know because these do behave different because they are a sequence. So we're plugging in 1, 2, 3, 4. And so we can treat them as sequences as we look at these limits. So the first one is using absolute value. It's a nice little trick. So if the limit as n approaches infinity of the absolute value of a sub n equals 0, then our limit would be 0. So if you take the absolute value of it and you take the limit and it approaches 0, well, then the limit goes to 0. So like this. Our a sub n absolute value would be this. And so you can see that alternating -1, which is giving us our issue, is going to be now disappearing because it's always going to be positive. So we end up with 1 over 2 square root of n. And so now we can take the limit of this, and if this goes to 0, then so does our general term. So a sub n absolute value would be the limit as n approaches infinity of 1 over 2 radical n. And you can already see right now our denominator is a radical n, so we know this is going to go off to 0. And so it's 0. So the limit of our absolute value equals 0, which means, and that doesn't equal 0, the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of -1 to the n over 2 radical n, is also going to be 0. So there's our limit, which is 0. And you can see this with Desmos. So we've got that alternating sequence going on. You can see how it goes back and forth between positives and negatives. So what's basically happening here is you can look at it this way. I'm going to plug in now the absolute value. That's our blue. So as we go down with the absolute value, right, it's approaching 0. Well, if you look at the bottom, it's also approaching 0. So coming in from the top and the bottom, we're just going to be approaching 0 from the top and the bottom, which means we are approaching 0. So by taking the absolute value, you're basically saying, well, let's just look at the positive version only. If the positive version of it goes to 0, well, the negative also has to go to 0 from the bottom. And that makes sense. So that's one trick, not trip. All right, factorials. If you see factorials, what you want to do is expand them out and rewrite them. So if you remember n factorial, this is just n times n minus 1 times n minus 2. And you can look at it the other way, all the way down to 1. It would be the same as 1 times 2 times 3 times 4, all the way to n. So if we have 2n minus 1, that means that's where we would start. And then you would just take 1 away, right? So that would be 2n minus 2. Well, where you want to start with these is you want to not start with the smaller of the two, but the larger. And you can see that the larger one will be on the bottom because it's adding 1, and the top one is subtracting 1. So this would be 2n plus 1 times, and then we take away 1. So that would just be 2n. And then we take away another 1. So you can see all I'm doing is adding -1 each time. So I'm subtracting it. So if I subtract 1, that 1 would disappear and give us 2n. And it subtracts 1. And I'm stopping there, and I can put factorial on that. See, as you go through any of these, you could say it's n times n minus 1 factorial. This would be n times n minus 1 factorial, because it's just going to continue from there on out. So we stop. This is what you do with factorials. And now on the top, you put 2n minus 1 factorial, and you can see where I'm going with this. They cancel. And we end up with 1 over 2n plus 1, and then now when we do the limit, as n approaches infinity of a sub n, we can use that instead. And I'm not going to even multiply this out or anything. We know that's 0. So that's how you handle factorials. We just cancel and see what we're left with. It'll tell you if it's convergent or divergent either way. All right, the next one is using our r to the n. So our sequence r to the n is convergent if it's between, the r is between -1 and 1. What we're looking for are fractions. So if we have a fraction here, then we'll end up with this. So I've got it here to where I can modify my r. This is our series, which we'll get into the next section. But right now we're just going to think of it as a sequence, just the general terms. You can ignore that number. But I want to leave it here just because of what it is. So a sub 1 is a number in front, but r is the most important. It's our base with our exponent of n minus 1 up there. So if you think about it this way, whatever the r is below here, you can see right now, as I move my n towards infinity, we're approaching 0. And I'm going to modify it now. You can see that it stays as 0 all the way here. Even you go, oh, it's not 0.3. Well, look, it'll go right back down to 0 here. So until I hit 1. Once I hit 1, it's just that horizontal line. So it is whatever a1 is in the middle, in the whatever our coefficient is. So it's 3. But right after 1, you can see now it goes off to infinity. So it is divergent. So if our r is bigger than 1, we're getting things like 2 or 3 or 4. And 4 to the power of n will be massive. So if you have something like this, 1/2 to the n, right, we're going to be going to 0. If you had 2 to the n, then you're going to go off to infinity. It's because this is a fraction. So if you think about a fraction to the power of n, it'd be a half of 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 a half. It's getting super, super tiny. So as we keep plugging our n values in, it gets smaller. So when you see exponents like this with the n, what you want to do is try to get them together so that you can find out what the r is. So you notice they both have a power of n, right? So we can rewrite this as 3 times 7 to the negative 1 to the power of n. And if you check it, we get 3 to the n and negative n. So now this would be 3 over 7 to the power of n. And you can see that 3 over 7 is less than 1. So if it's less than 1, right, between negative 1 and 1, we know that this is going to go off to 0. So we can say now the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of 3/7 to the n, which would be 0. So again, if that r here is bigger than 1, it's going to become divergent. So if that had been a 2 to the n, it would go off to infinity and it would be divergent. But the key is to get it together as one base. All right, here's our last one, and it's just a nice little tricky one, just to show you what our tricks from before still apply. So we do n infinity of a sub n. It's going to be a little bit of rewriting. So if you look at this, you can already see that if I were to plug in infinity here, this would go to 0. So we'd get sine of 0, right? We'd get sine of 0, which is 0, but that's still going to be infinity. So we rewrite it. We go, okay, well, if I can convert that into something like this. So it's all about playing with these problems and looking at it. Now they're the same, but then that would go to 0 and that would go to 0, right? Well, now what? Right? Because now we have 0 over 0. Well, if you notice something, they're both going to 0. And we have a nice special rule. So we can take this now and say the limit as t approaches 0, and we got to put plus on there because we are coming from positive infinity. And then we put sine of t over t. And what we did is now convert it. So we've taken n to infinity, and now we're taking t to 0. So we're not really changing the limit, we're just modifying it. But I like to call it changing the limit. So if you remember this little rule, limit of t approaches 0 of sine of t over t is 1. And you're done. So these problems will just take practice, and it's good to have a note page, which I've given you already with a lot of this stuff in it, but add to it any little tip or trick that you figured out. Like remember L'Hopital's rule here. If that works, then you can use it as well.